So, for the keyboard interface, we have seen that for initially we have to check whether all keys are released or not, and that is done by the first part of the code in this region where I am doing that thing. So, it is we are checking that whether all keys are released or not. So, once we have seen that all keys are released, so this JNE is has failed. So, we have come to the next point. Now, I have to make one of the rows as 0 and check whether any key has been pressed on that line. So, we do this by putting the pattern EF hex onto the port P1. So, EF hex means these all these bits are 1. So, they are F and this is also so these bits are all 1 and this bit is 0. So, this bit being 0. So, we will be getting the so accordingly. So, any key pressed on this row, if any key is pressed on this row. So, accordingly that corresponding bit here will become 0. So, after outputting this, so we are getting this and then we are checking the bit P 1.0. So, we are checking this particular bit. So, if this key has been if P 1.0 this bit becomes 0 now after doing this output. So, then it is that the key pressed is bit 0. So, then we go to this dB 0. So, dB 0 will be so dB 0 is here. So, now we need to check that whether it was an error or not. So, that check is done at this point. So, we call for a delay of 10 millisecond, we wait for 10 millisecond and after 10 millisecond we again check with the bit 1.0. So, if the bit becomes 1 by this time, that means it was a noise. Okay. So, that was a flicker. So, it is not a valid bit. So, in that case we will be going back to scan 1. So, scan 1 is here. So, this point. So, again it will be going back to this point and again we will check whether this bit is pressed or not. So, in this way it will be going back to the previous point and then we will be moving. So, if the bit has been pressed, if the key has been pressed, then this we are moving the value 0 to A and A register and then LJMP gate code. So, LJMP gate code here I will be getting the corresponding ASCII code. So, in this key table is defined like this. So, in individual bytes. So, key table is a memory location from where I will be storing the ASCII values 0 to F. So, those key values are stored and this A value, A register value will be used to index into this table. So, what is done? From in the DPTR register we load the value of key table, then moves the A comma at the rate A plus DPTR. So, if the 0 key has been pressed, then it will be coming to the first location of this key table. So, you will get the character 0. On the other hand, if the 1 key was pressed, so if we just go back, if this key is not pressed, then we are checking the next key, the scan 1. So, we are checking for whether the next key has been pressed, the 1 has been pressed or not. So, if 1 is pressed, then it will be so we have to say that okay, we have to put the code of 1 into the accumulator. So, that is done here. In DB1 you see that we wait for 10 millisecond, then again wait for then again read the value of 1.1. So, if 1.1 is 0, so if this is if this is 0, that means the key 1 has been pressed. If this bit is 1, that means the key is not pressed. So, it was a noise. So, we go to the scan 2. So, scan 2 is actually taking us to the next point. So, scan 2 is here where I am checking for the next column. Okay. So, this way this routine continues. Okay. So, now we have got this A register will contain the value of the key that has been pressed. So, after all these are done, then we will have then we will have to go back to this point again. So, where we will be so we will be outputting DF hex. So, we were previously we were outputting EF hex where this this bit was 0 and rest of the bits were 1. Now, I am putting DF. DF means so this bit will be 0 and these are all 1s. So, now this 1.5. So, this particular row I am checking and then again the same thing. Okay, the similar code will repeat, but the numbers will be different. Now, if you find that say dB 0. So, when you are doing this check 1.0. So, when you are checking this pin. So, if this bit is 0. If this bit is 0 means this key has been pressed. Okay. So, this key has been pressed. So, we can jump to the DB4 routine. So, then we jump to the DB4. So, this we will have a similar such DB4 routine which is not shown here for the sake of brevity. Now, so this in the key table we are storing all the key values. So, this key table you see that it is something like this. In the key table it is a part of the memory where I have stored all the key values. So, in the first location of this key table we have got the ASCII code of 0, the character 0, then the ASCII code of character 1, then the ASCII code of character 2, and then finally, we have got, since up to F is there in the ASCII code in the hex keyboard. So, we will store up to the character F, and then so this is the key table. So, this is the key table. So, this is so success. So, it will have some address, say this address is say 2000. So, from 2000 onwards these values are stored. So, when I am first in this get code routine, we first getting this hash key tab into dptr. So, dptr becomes equal to 2000, and then we are adding with dptr the value of a. And if you look into this part of the routine, you can understand that in the a register we are holding the key index, okay, that has been pressed. So, that is there in this a register, it is added with dptr. So, if you have pressed say key number 4, then a is equal to 4. So, dptr plus a will take us 2000 plus 4, it will come to the location 2004, and in 2004 I will have the character 4 there. So, character 4 will be stored there. So, ultimately a will get that character 4. Then it will again jump to, so we have got the character 4 here. So, we can do some processing with that character which is not shown here explicitly, but as far as keyboard routine is concerned, so it will go back and it will again check whether all keys are released or not. So, it will do that. So, like here it is jumping back to this RELS. So, RELS is here. So, it is jumping back to this point to see whether all keys are released or not. So, this way we can very easily interface a keyboard, here the hexadecimal keyboard with any microprocessor or microcontroller based system. Next, we will look into output device. So, we have seen the keyboard as an input device. So, next we will look into output device. So, output device we can connect some LED, which is the most common output device. So, this may be one type of connection. So, here we have put a current limiting resistance here, then that is LED. So, if you to glow the LED, you should put a you should get a 0 at this point. So, if you put a 0 here, then there is a current flowing path and the LED will glow. So, that is one type of connection. Second type of connection is like this, where the limiting resistance is missing. But if you do this, then there it is dangerous, because a high amount of current will flow through this line when this bit is 0, port bit is 0. So, this will you will get a high range of high value of current flowing. So, the LED may burn and the port pin, the port of the microcontroller or microprocessor may also get damaged. So, this is never recommended. Okay. So, this is not recommended. And the third connection, where I have got this port pin giving a value of 1, and that is actually making this LED on. Okay. So, this connection, okay, this is this may be fine, but this port pin they normally drive very low current. So, they do not have high current. So, the LED may not be glowing very brightly. Okay. So, we have got 3 different cases. In case 1, LED is on if output is 0. Most of the LEDs they will drop 1.7 volts. So, you can find out, so for a LED to glow completely you need about 10 milliampere of current. So, you can find out 5 minus 1.7 by 470. So, that is nearly 10 milliampere current you will get here if you put a 470 ohm resistance at this point. Case 2 is not advisable. Case 3, normally we do not get more than 1 milliampere current. These port pins they do not drive high load. So, the current values are not that high. So, the LED will be dim. So, the visibility may be a problem. So, the first connection is better. Okay. The next display that we will have is a 7 segment display. So, this is also very common, but like say digital watches and all that. Of course, many a time now we have got LCD displays, but LED displays are less costly, and that way we have got 7 LEDs arranged to form the number 8. So, this is the structure. So, we have got these LEDs A, B, C, D, E, F, G, and sometimes we have got another LED. So, instead of 7 segment it will be called 8 segment. So, where we have got another LED here. So, another LED at this point. So, which is the dot. Okay. So, we have got a dot here. So, that is often called the bit H, but so that can display a more variety of digits and letters. Some of the characters can be displayed, not all. So, what can we do if we want to display some pattern? We can turn on the corresponding portions. Okay. Accordingly, we can get a digit or a character displayed. So, there are two types of 7 segment displays. One is called common anode, another is called common cathode. So, this common anode means all the anodes they are tied together, all the 7 LEDs their anodes are tied together and they are driven by a single line, and then all these cathodes. So, if you want to glow a particular segment, you have to give a high value here and you have to ground the corresponding LED, corresponding diode. Okay. So, for example, if you want to glow say this LED only, so you have to give a 1 at this point and you have to give 0 here, whereas for the rest of the lines here on this side. So, you will put a 1, so that these LEDs do not glow. On the other hand, this common cathode configuration. So, here this side the cathode part is common. Okay. So, this can be connected to some ground pin, to some ground line, and wherever whichever LED you want to turn on. So, you have to put a 1 there. So, that way, so that light will be 1. So, these are the two different configurations, common anode and common cathode. In case of common anode, cathode lines are connected to the output, and in case of common cathode, anode lines common cathode is common anode is connected to the output. So, here also the common cathode is connected to the output. Here the contact cathode will be connected to the output, and here the contact anode will be connected to the in this case contact anodes will be connected to the output. So, this is wrong. So, this is wrong. This should be contact anode. So, this contact anodes will be connected, and this is in this case contact cathodes will be contact and cathodes will be connected. So, this one. So, this variety is better for interfacing purpose. This common anode variety is better, because here you can put a 1 and here you can put the values 0, whereas in this case you have to put so many resistances for doing that. For interfacing purpose, this one will be better. So, a resistor will be needed to control the current. So, this is in common anode configuration. So, I will connect this resistance, a single resistance will be sufficient, and they will be giving current to all the 7 segments of the display, and this in the 8051 port I will put the corresponding bit to 0, so that the corresponding LED will glow. On the other hand, in the common anode configuration, we will see that we will give the supply voltage, and now individual LEDs. So, they are having their own resistors. So, in this case the current that will come. So, the current that will be there. So, that will be limited by this resistance, and that current will be divided among the LEDs that will be on. So, for all the bits that are turned on, the current will get divided between them. So, as a result, all the LEDs may not glow very brightly, because the current getting divided. So, the brightness may be a problem. When if only one LED is on, others are off, then that LED will be glowing very with a good brightness, whereas if say all the LEDs are turned on, then all of them will be glowing, but the output may be dim. On the other hand, in this case we do not have that problem, because these LEDs currents are controlled separately. We have got the separate resistances. So, the currents are controlled separately. So, we have got this brightness will be better in this common anode configuration. So, that is why we said that the common anode configuration is better for connecting the LEDs. So, how do we do this thing? How do we do these connections? Okay, interfacing one DIP switch and one 7 segment display to the LED, so to the 8051. So, maybe with the port 3 we have connected 4 DIP switches, okay, and with this and they, so 3.0 we have got this active pull up resistance. So, that way the pull up resistances are there. So, you if you keep it open, then the bit port bit is automatically 1. So, we can use that philosophy, and we can, if we want to put a 0. So, I have to close the switch, accordingly that bit will become 0. And this particular display, so this 1 point this P 1.0 to 1.7, these bits, so they can drive this 74240. So, that chip. So, this is and this is a driver for this 7 segment display, and you can put the value here, accordingly this the corresponding segments will be glowing, this A B C D E F. So, this actually outputs this A B C D E F G and this dot point D P. So, this driver can be used for that purpose. So, we can have a lookup table like this. If you want to display the digit 0, then the segments that should glow are A, B, C, D, E and F. So, this A, B, C, D, these will be on, G and H, G and P. So, those are off. Okay. So, accordingly the hex code is 3F. Similarly, if it is 1, then only the segments F and E, they will be turned on, rest are 0. So, accordingly the code is 30. So, this way you can find out the hexadecimal codes for all the characters that you want to display on your system. Fine. So, this way the program is now very simple. So, from the port P3 we get the value into A register, and then we AND logical A with 0F hex. So, that way we can get the content from port 3. So, like here. So, we can just get these 4 port bits into the A register, and then since this 0, 1, 2, 3 is only there. So, we have to mask out the higher order bits. So, that is done here by doing this 0F(x), this higher order bits will be masked off. Then this move DPTR comma hash 7s table. So, 7s table will have the 7 segment things like all these numbers 3F, 305B. So, whatever patterns are there. So, they are stored from this 7s table onwards. So, that value will be moved to, so DPTR will get the value of the key that is pressed. So, 0, 1, 2, 3. So, those keys will be there. So, that will be added to this DPTR, and here we have got this the number that I want to display, that should be entered through port P3, that one single digit. So, though it is the number, so you can enter 0 to F that way only. So, the number will be entered on port P3 as a binary coded decimal digit, and then we will get that corresponding code from the 7s table, and that will be moved to the port P1, and on port P1 you can get that the corresponding display. So, this way we can interface 7 segment display with the this 8051 chip. Next, we will look into another very well known interface chip, which is known as programmable peripheral interface or PPI chip, which is 8255. So, this is needed because your 8051, if you see carefully, then 8051 has got 4 ports P0, P1, P2, P3. Out of that, only port P1 is totally free. P0 and P2, so they are used for this connecting external memory. So, this address and data bus lines are there, and for port P3, so that is multiplexed with many other functions. So, that creates difficulty. So, if you in your application, so if you need to connect both external memory and some peripheral device, then we do not have much option left, because we do not have enough port left for that purpose. So, if you connect one 8255 chip with the system, so it makes the you get a number of ports available, and they are very easily programmable. And also, if you look into other processors like 8085 and all that, where we do not have any IO port directly. So, you can of course use these in out instructions to read the values directly from the data bus lines, but the data bus lines are hanging in that case. Okay. So, that is another problem. So, we have to do something so that we can get some buffered input output. So, 8255 will ensure that type of operation. So, this is the pin diagram of 8255. So, it is a 40 pin dual inline chip. So, you see if you look into this bits that we have, pins that we have got port A pins, port A0, A1, A2, A3, A4, A5, A6, A7. So, port A is an 8 bit port. Then we have got another port port B. So, PB0 to PB7, then port C PC0 to PC0, 1, 2, 3, 4, 5, 6, 7. So, that is again another port. And then so these are the 3 ports that we have in 8255, and for getting the values into 8255. So, there are lines D0 to D7 which can be connected to the data bus of the processor. For selecting the chip, you have to make this CS bar pin low. So, you can have some appropriate decoding logic by which this CS bar pin will be activated. So, you will get this 8255 will get selected by that. And if you and also there are some internal registers and this ports. So, for selecting internal registers and ports, so you can select this A0 and A1 bits accordingly. So, they are normally connected to the A0 and A1 bits of the CPU address bus, and from there we get the value, we control these individual registers. And then these read bar, write bar lines are there for doing read or write operation for the ports. So, at a block diagram level, so you can say that 8255 it has got 3 8 bit ports A, B and C. They can be programmed as to input or output, or can be changed dynamically. Okay, it is the structure. So, you can just change some control word setting of 8255 by which these ports will behave in different fashion. So, you can program it as input port, you can program it as output port, and you can also program it as bidirectional ports in some cases, some limited cases, and also you can program some of the port bits to be bit addressable. By individual bit setting can be done. They also have handshaking capability. So, if you are connecting a number of devices with your say microcontroller or microprocessor, you want to connect some devices, so that data transfer will take place via handshaking, then this can be done. Okay. So, this 8255's handshake mode can be utilized for that. Other important pin lines that we have D0 to D7, read bar, write bar, A0, A1, CS bar and reset. So, we will see their utility. So, this port PA0 to PA7, so these are 8 bit lines for port A. So, they can be programmed as all input or output, or all bits as bidirectional input output. So, this is, so you cannot do a bitwise programming for port A. So, this entire 8 bit has to be programmed either in input mode or in output mode or in bidirectional mode. Then this PB0 through 7, so they can be programmed as input or output, again the same thing, but it cannot be used as a bidirectional port. So, only port A can be used as bidirectional port, port B cannot be done that way. And we have got port C. So, port C is PC0 to PC7, again this is an 8 bit port. So, again all can be done as input or output. So, it again it cannot be put in bidirectional mode, but this port C can be splitted into 2 ports. So, we can say port C upper bits and port C lower bits, CU and CL. So, upper bits are PC4 to 7 and lower bits are PC0 to 3. So, each can be used separately for input or output purpose, and these bits of port C, they can be programmed individually. So, this has got that bit addressability feature. So, if you are using say 8085 type of microprocessor where you do not have bit addressability of ports, so you can connect one 8255 chip with that, and then you get some bit addressable locations for input output. Then we have got this read bar and write bar lines. So, these are 2 active low signals that are used as inputs to 8255. So, read bar and write bar. So, they can come from they may come from 8031, 8051, and they may be connected to those inputs. Then we have D0 to D7. So, they are actually D0 to D7, they are data pins that we can connect to the microcontroller. So, you can send data packet to the 8255, or you can get the data packet back from them. like you may want to control some of the port configuration, that way you want to output something to the 8255, or if a particular port is configured as output, so you want to send data to that port. So, that way you can send the data from microcontroller or microprocessor through this D0 to D7 to that port, or if a port is configured as input port, so you can transfer the content from that input port to the microcontroller by that. Then we have got this reset. So, reset is an active low, active high signal. So, this is used to control the register. So, to clear the control register. So, all ports will get initialized as input port. So, this is the default configuration. When you reset the 8255 chip, all ports are configured as output ports. So, if you sorry, as input port. So, if you want to operate 8255 in input mode only, so you do not have to do any control word setting. So, you can start directly, but if you want that this has to be some of the port bits should be output, then we have to put some control word in those things. So, this way we can use 8255 for various operations, and we will see some examples by which we can do this interfacing.